Welcome to AP Calculus. This is the first set of videos we'll be doing, learning about Unit 1, Limits, Continuity, and the Squeeze Theorem. Section 1.3 is all about continuity. Let's talk about what continuous actually means. For a function to be continuous, it means there's no holes, gaps, or jumps in the graph. Basically, it's saying that I can trace the entire graph without picking my pencil up. Let's look at the formal definition. A function is continuous at a number c if the following conditions are met. F of c is defined, where c is in the domain. The limit as x goes to c of f of x exists. And the limit as f goes to c of f of x equals f of c. We'll be doing several examples, and I think that will make this definition of continuity a lot more clear. On page 103 in your book, there are several graphs, and they really walk through something being continuous and not continuous, and when each one of these pieces of the definition are met or are not met. So let's take a look at example 1, also on page 103. Determine whether f of x equals 3x squared minus 5x plus 4 is continuous at 1. The first thing we need to do is check if 1 is in the domain. And since we don't have any domain restrictions here, 1 is in the domain, so that piece is good. Next, we're going to look at what is f of 1. That'll be 3 times 1 squared minus 5 times 1 plus 4. So let's see, 3 minus 5 plus 4 is 2. So f of 1 is 2. Now let's look at the limit. As x goes to 1 of 3x squared minus 5x plus 4. And we'll plug that 1 in. And again, we get 3 times 1 squared minus 5 times 1 plus 4, which is 2. So here we have the limit exists because it equaled a number, and the limit of the function equals the value of the function at x equals 1. So then yes, this is continuous. Now let's take a look at this next one. Determine whether g of x equals x squared plus 9 over x squared minus 4 is continuous at 2. Now right away, hopefully you can see that there's a problem here. At x equals 2, what does g of x equals? So let's plug it in. 2 squared plus 9 over 2 squared minus 4. So let's see, that's 13 over 0. Oh no, that's bad. We're not allowed 0 in our denominator. So that means 2 is not in the domain because our denominator equals 0 at 2. So not continuous. Or discontinuous. Example 2 on section 1.3 and page 104 asks us to determine for this function if it's continuous at -2, 0, and 2. So hopefully right away you see that my denominator of x squared minus 4 is going to be 0 when x equals 2 and -2. So at these 2 points, the function is not continuous. But let's take a look at x equals 0. What is f of 0? 0 squared plus 2 over 0 squared plus 4. So it looks like it's going to be the square root of 2 over 4. And then let's look at the limit. The limit as x goes to 0 of f of x. It's going to be the same thing, 0 squared plus 2 over 0 squared plus 4. So since the function equals the limit at x equals 0, and 0 is part of the domain, then the function is continuous at x equals 0. So this example is a good problem that points out that we have certain points of a function that we may be discontinuous at and certain points of a function that we may be continuous at. right, let's take a look at example 3 on page 104. Here we have a piecewise function. Now we could graph the function, or we could, to help us illustrate what's going on, and we might do that in a minute, or we can go through our definition. As we can see, every number is defined. We have something that happens less than 3, when it equals 3, and greater than 3. So all of these are defined, so I know that they're all within the domain. But let's take a look at the limit of each of them and see what happens when we get f of 3. So f of 3 is going to be 9 because when x equals 3, the f of x value is 9. Let's take a look at the limit from each side. What's the limit as x approaches 3 from the left? Well, from the left would be the numbers less than 3. That's going to be this first piece. Let's see, we have x squared minus 9 over x minus 3. Now, when I try direct substitution into this, I'm going to get 3 squared minus 9 over 3 minus 3. Now, that will be 0 over 0, which is my indeterminate form, which lets me know that there's another way to do this problem. And the other way, hopefully you can notice, is factoring. I can factor x squared out of x squared minus 9 into x minus 3 and x plus 3, all over x minus 3. So now I have my limit as x goes to 3 from the left of x minus 3 times x plus 3 over x minus 3. My x minus 3's will cancel, and I get the limit as x goes to 3 from the left of x plus 3. I'll do my direct substitution. I get 3 plus 3, which is 6. And now I can stop right here. I don't even have to continue and look at the other piece because 9 does not equal 6. Therefore, this function is discontinuous at 3. If we want to do a quick sketch of the graph, it would look something like this. We'd have a straight line, and then a hole, and then our parabola, and then we'd be filled in up above that hole if this was 3. And you can see that we're definitely approaching the same number from the left and from the right, so our limit would be able to exist, but the function is discontinuous because that dot does not fill the hole in. In the previous slide, I just alluded to filling the hole in. That's called a removable discontinuity. It's when I could substitute one number in and just block off it from being discontinuous. So the formal definition is let f be a function that is defined everywhere in an open interval containing c. The number c is a removable discontinuity of f if the function is discontinuous at c, but the limit as x goes to c exists. The discontinuity is removed by defining the value of f at c to be the limit as x goes to c of f of x. So in the previous slide, if our piecewise function was defined as 6 instead of 9, that would have filled in that hole and made the removable discontinuity continuous, and the whole function could have been continuous. Not all continuity problems can be removed like this hole, but holes can be filled, and those are the type that we can fill to make something continuous. Now, one-sided continuity, it means that the function approaches the same number from the left as the function value, or approaches the same number from the right as the function value. In order to be continuous overall, we look for all of these points to be hit. The left has to equal the function, has to equal the limit from the right. So when I look at example 5 on page 106, it's asking me to determine the continuity on a closed interval from -2 to +2 of f minus x squared. So first let's think about what happens between the two values of -2 and 2. So if I pick any c in between -2 and +2, is it going to be true that f of c is going to equal the limit as x goes to c of f of x? Well, let's see. F of c is going to be the square root of 4 minus c squared. And let's take a look at the limit as x goes to c. So that's going to be the limit as x goes to c of square root of 4 minus x squared. and we can substitute in, do direct substitution of 4 minus c squared, all in my square root, and yep, those look exactly the same. So any number in between -2 and +2, it looks like the limit is going to be the function value. Let's take a look at the endpoints though. That's going to be really important to determine what happens at -2 and at +2. The graph might be instructive here. So we have this semicircle, we're only looking at the positive part. So we have the semicircle on 2 and at -2. And we've already established that everything in between is all good. Everything in the middle here everything in here on the circumference of the graph of the circle is perfectly fine. That was our C in between. And now we're going to take a look at these endpoints of -2 and +2. So let's take a look as the limit approaches -2. And as we do that, we're coming from the right if we're following the graph. So that's going to be from the right. The limit as x approaches -2 from the right of our function, 4 minus x squared, is going to be 4 minus -2 squared. And the square root of that will be the square root of 0, or just 0, which is also the same as f of -2. Same, 4 minus -2 squared. So far we're doing great on our continuity. Let's take a look at the limit as x goes to 2, +2. And this time we're coming from the left. It's going to be a similar story here. The limit as x goes to 2 from the left, square root of 4 minus x squared, which will be the square root of 4 minus 2 squared, also 0. And we see that f of 2 is exactly the same at 0. So since all the numbers inside the domain were defined and the limits equaled themselves, the function values I mean, and the endpoints worked, then yes, we are continuous on the closed interval -2 to +2. Now these properties of continuity look very similar to the properties of limits. And of course that's because limits are so closely linked with a function being continuous. So I'll give you a second to take a look at this slide. All these properties can be found on pages 108 and 109. But let's use them, put them into action. When I think about where a function is continuous, I actually think about where it is not continuous. So when I look at square root of x squared plus 4, I'm thinking, where is that not defined? Well, I know that if I'm under a square root, the radical must be positive. So I know that to be in the domain, square root of x squared plus 4 must be greater than or equal to 0. So if I square both sides, I know x squared plus 4 must be greater than or equal to 0. So x squared must be greater than or equal to -4. And then I'll take my square root of both sides. Oh, but here's my problem. I can't take a square root of a -4. Therefore, I don't have any problem with my domain because there's no numbers that make this not work. So my domain here is all real numbers and it's continuous on all real numbers. This symbol is a symbol meaning all real numbers. So if you're new with that, please become familiar with it. It's a nice shorthand for all real numbers. I'm going to approach part B the same way. I know underneath my square root I have to be greater than or equal to 0. So let's see, I'm going to move that 1 over, and x squared has to be greater than 1. So x has to be greater than or equal to the square root of 1. And as we know, when I take the square root of 1, I also have to look at the positive and the negative. So we're going to be greater than the positive 1, and x is less than or equal to -1. That's the domain of this function, and that is also where it's continuous. I'm going to write it a little bit neater. So x is less than or equal to -1, and or union, x is greater than 1. In part C, we have a couple different things going on. I have this fraction of x squared minus 1 over x squared minus 4, and I have a square root. I'm going to have to look at the continuity of both of them and the domain of both of them. So let's see. For the domain of x squared minus 4, the fraction, I'm going to set that equal to 0 because I know my denominators can't equal 0. So my x squared can't be 4. So my x can't be 2 or negative 2. And when I look at the square root function, I know that has to be greater than or equal to 0. So x minus 1 has to be greater than or equal to 0. So x minus 1 is greater than or equal to 0. So x has to be greater than or equal to 1. When I put all of this together, so when I think about this domain, I have to look at it as a big picture. X has to be greater than 1, and it can't be negative 2. Well, that kind of gets thrown out then, because x is greater than 1 does not include negative 2. So we kind of throw that away. We're going to start at negative 1. And if we're doing set notation, that's going to be a square bracket, which lets us go from 1 to 2. And now will be an open bracket because 2 is not included. Union, and we're going to go from 2 to infinity. So let's talk about what these pieces mean. This square bracket means including 1. This open bracket means not including 2. And then we always have an open bracket at infinity because there is no end, so we can't ever include the last point of infinity. On the AP exam, it's not really told how you have to say things like this. You can use set notation, as I did here. You can use greater than or less than symbols, or you can use words. As long as you get your point across and you're clear, it doesn't actually matter which way you represent what you're talking about. Now, the intermediate value theorem is something that's super important, and it's one of those things that looks way more complicated than it actually is. So I'm just going to read it to you, and then we're going to talk about what it means in actuality. Let f be a function that is continuous on a closed interval a to b, and f of a does not equal f of b. Then n is a number in between f of a and f of b. There is at least one number c on the open interval a to b, for which f of c equals n. Now that looks super complicated, but it's actually not that bad. The intermediate value theorem says, if I go from 0 to 60 in my car, I had to hit every number in between. There had to be at least one point where I was going 10 miles per hour, 30 miles per hour, 40 miles per hour, all the way up to 60 miles per hour. I could have come back down and gone up and down. So in my example of going 0 to 60, it could have been a straight line like this, or it could have been wavy lines that got me up to 60. And therefore, I might have hit 30 miles per hour a couple of times. But I had to hit it at least once. I don't get to go from 0 to 60 and not hit every number in between. All right, so we know that this is continuous. We have no restrictions on our domain. So we just need to make sure that f of 1 and f of 2 are going to be different numbers. So f of 1 is going to be 1 cubed plus 1 squared minus 1 plus 2. So let's see, that's 2 minus 1 plus 2 negative 1. And f of 2 is going to be 2 cubed plus 2 squared minus 2 plus 2. Let's see, 8 plus 4 is 12. Since f of 1 does not equal f of 2, and I know the function is continuous on this domain from 1 to 2, therefore, by the intermediate value theorem, we must hit every single number between 1 and 2.